Morning everyone. It looks like a couple of people might still be logging in, but I thought we might get a start, try and keep on schedule. So my name's Brodie McDonald. I'm an application engineer at Leap Australia, and today we're going to be going through basically start to finish the process that you would take to do some composite analysis within the ANSYS Workbench environment, and we'll be really focusing on a tool called the ANSYS Composite PrepPost, or ACP. So I'll just start off with the agenda. We're going to do a quick introduction to composites in general, and then have a look at the ANSYS Composite PrepPost workflow. I'll quickly show you a demo of that, and then we'll move on to the real kind of meat of this training, which is we'll actually go through ACP, and we'll look at doing a composite layup definition from start to finish. This ought to take about half an hour, and then I'll give you a demo on a composite chassis model that I have. We'll take a quick break for lunch, and then we'll move on to actually using this composite definition to do FEA analysis, and then pre-processing it with some of the composite-specific tools inside ANSYS. And then finally, I'll look at some of the advanced topics and give you a quick demo on the nonlinear composite damage that we can introduce into our model to take it to a greater level of detail. So just before we begin, a little bit of kind of definitions, a few definitions, so we're all on the same page. So composites, what is a composite? It's just a material that's made up of two different materials. They can take a lot of different forms. Generally, the two materials will serve two very different purposes. One's going to be called, one will be referred to as the reinforcement. This is generally a very strong fiber or meshing that we're embedding in something that we're going to call the matrix, which is generally a more flexible material, something that gives it the structural form but doesn't carry a lot of the loading, at least under normal conditions. So another feature of composites, composite structures in particular, is that they're generally built up from lots of individual layers of these materials. And we're varying the orientation of each layer to give it the strength and performance that we're looking for. So just a couple of examples of the materials that we might be dealing with. On the left here, we have woven glass fiber. So this is just the fiber. It's all dry. This has been woven together in a 0-90 configuration. So you would generally lay this up over a mold, and then you would impregnate it with a resin. So that might be an epoxy resin. We're forcing glue through this to turn it into a solid structure. These are flexible at the moment. Similarly, woven carbon fiber. So this is just a stronger fiber, stiffer fiber. You could use the same epoxy resin and would turn this into our structure. And then finally, on the right-hand side, this is a unidirectional carbon fiber. So instead of having that 0-90 configuration, we've got all of the fibers running in a single direction, left to right. I might be referring this to a UD carbon fiber in some of the later slides. So just the terminology, I mentioned before, the matrix, that's the homogeneous base material that forms the bulk of the composite layer material. So it's basically holding these fibers together, giving it its form, but generally won't be taking the majority of the loading. And then on the flip side, the fibers, so these are going to be embedded into the matrix, and these are really what gives the composite its characteristic anisotropic response. So what anisotropic response is because these fibers could be running in a single direction, or they could be running in a number of different directions, the response of the structure is different depending on which way you pull it or push it. So a laminar is what we would call a single layer of a composite. I might obviously call this a layer or a ply, so a single ply of material, and then we would build up these plies into a laminate, and that's going to have information in it such as the stacking sequence and the orientations. So applications of composites, particular to your kind of environment. So chassis are a really good application for these materials. whether it's a complex kind of monocoque structure from this F1 vehicle or a Formula FSAE type monocoque chassis with the suspension and the engine substructures mounted to it. The aerodynamic surfaces on a vehicle lend themselves pretty well to being manufactured out of carbon fiber, or composites in general, I should say. That's really because we have a lot of flexibility in the way that we create our structures rather than metals, which are very difficult to machine and get into the final shape. We can do some pretty crazy stuff with the composites because we build it up from something that's quite easy to handle, that we can force it into some pretty interesting shapes. So this is just a front wing and then also a rear diffuser, and you'll notice that this rear diffuser actually has some sandwich panels built into it, which is another really big benefit of composite materials. Also some suspension components. So these long, slender members, it's very easy to just go and almost buy composite materials off the shelf, and we can generally replace any kind of metallic structure that might be integrated into the suspension and just replace it with a composite, saving weight, more strength. It's all good stuff for you guys. And then another really interesting application is wheels. And it's interesting because, so these are generally rotating when they're in action. And what that means is that if we can reduce their weight from a static perspective, as in when they're not in use, we actually get disproportionately higher reductions in rotational weight, which is really good for cornering, braking, acceleration, things like that. And then obviously there's loads of other applications. Basically anything that we're demanding maximum strength and stiffness for a minimum weight. So in applications like a high performance vehicle, that's everything. So we want everything to be as light as possible whilst remaining safe. So maximum strength and stiffness is obviously something that we need to make sure we maintain. So applications, let's talk about some of the benefits of why people are using these composite materials. One of the biggest things that you can see when we're looking at composites is they have an incredibly low density. So they're about 15 to 20% lighter than aluminium. That's actually about 3 times less than steel. So you can see someone going from a tubular steel space frame to monocoque, composite monocoque. That was a 40 kilogram reduction in a single year. Pretty impressive numbers. And this really benefits things like acceleration, braking, cornering, as well as fuel consumption. So all good performance indicators that we're looking for in a high performance vehicle. Another big benefit is high strength. So when we're looking at a unidirectional carbon fiber, so I'm talking about loading these fibers along their length, their yield strength is incredibly high, over 1,000 megapascals. So there's very little competition in this area for a material which is 3 times lighter than steel and has, at least equal to better strength. That will result in a really good specific strength, which is strength divided by weight. I mentioned it earlier. One of the other benefits of composite fibers is composite materials is how we can manufacture our structures. So I mentioned because it's essentially flexible when we first start out with it, we can force it into some really interesting shapes using molds quite easily, and then we just set it hard. If we were to try and machine this out of metal, it's really not practical. And then the other thing that they lend themselves incredibly well to is integration into a sandwich composite, where we would have face sheets of composite material. In this case, it looks like woven carbon fiber. And then we have a low density material in between, which is just giving us room between the two face sheets. And what that does is increases the stiffness just a lot. So we're talking about relative stiffness to a solid metal sheet. The moment we introduce this sandwich composite structure and we make it twice as thick, we're talking 7 times more rigid. 3.5 times stronger and a very, very negligible increase in weight. So this technique of integrating sandwich structures into your vehicle can just improve the stiffness of the vehicle just a lot. There's a lot of other benefits. Just rush through them now. High stiffness. The Young's modulus of carbon fiber is about the same as steel and is about 2.5 times more than aluminium. So that's good because the elastic region is where you want to be operating your vehicle in, obviously. So that stiffness is really critical to your performance. So fatigue resistance, also very, very good. High dampening properties. So if you've got an engine shaking your vehicle, it's going to be reducing the forces that your driver's feeling. So that's good for them. Fabrication diversity, I mentioned that before. And then thermal properties. Composites are very stable under elevated temperatures, elevated and reduced temperatures. So we're not going to have any of the deformation when your structures are heating up, maybe under just radiant heat coming off the engine or something like that. It's not all good news. There are some complexities that are inherent in composite materials, and it's things that we really need to look out for when we're analyzing them in the finite element analysis. So one of the biggest things is that the scales across composite materials that we need to deal with. Some of the structures that we're talking about, I mean, they're huge. We can create an entire aircraft or an entire boat, or in this case, a wind turbine out of composite materials. We're talking, meters, tens of meters in length. But when we look at the actual response of the material, it's governed by things that are sub-millimeter sizing. In this case, microns, 5 microns. And we're looking at, so this is some scanning electron microscopy of a composite material. So these circles are the fiber itself, and you can see it embedded in the matrix. And so the failure of this material is actually governed by this tiny little crack, which actually is running its way through the matrix. So we need some way of understanding material response at these tiny little tiny little scales, which we can then efficiently scale up to the full structural size. And where you'll generally find is the kind of sweet spot between detail and computational efficiency is what we would call the mesoscale. So we're actually looking at individual plies. So this ply thickness, it's in the range of about 0.2 millimeters. So if we can design our structure from a level of detail of ply, like per ply, we will be able to analyze some of these ginormous structures efficiently. So another complexity is the highly orthotropic response of these type of materials. So I mentioned it before, when we're looking at a composite material, generally we'll have long fibers aligned in a specific direction. And so if you're loading the material along those fibers, it will be incredibly strong. It will be incredibly stiff. If we then begin to load that material off axes, that is, so if we pulled it at right angles to the fiber, we're going to have a huge drop off in the strength and the stiffness, because all of that loading is all of a sudden being carried by the matrix, not the fibers. So here we have the tensile strength of glass epoxy and carbon epoxy compared to the fiber angle. So if we're pulling it along its length, it's very strong, over 1,000 megapascals. As we slowly pull it off axes, when we're getting to just a 15% misalignment from loading those fibers, we've already lost, we're down to a tensile strength of about 200 megapascals. So we need to either factor this into our design, or we need to have a level of detail in our design that we know the loading directions on our fibers quite accurately, and we know that the structure is still going to be safe. The same kind of trends in the Young's modulus. It's going to drop off very quickly with that loading misalignment. So manufacturing, it is one of the benefits of a composite material, but it can also be one of the complexities. It's very labor intensive. It's very reliant on the quality of manufacturing, the performance of the structure. And there's a lot of things that we need to take into account when we're thinking about how we manufacture these materials. And this is a couple of really good examples. So we have quite a large mold being laid up here with looks to be woven carbon fiber. So they're laying this sheet in and they're pressing it in. That this doesn't have any resin in it yet, but you can see that we have this wrinkling of the material at certain locations. And this is inherent in the mold design, but it's also because we're dealing with fabrics. Fabrics, if we fold them incorrectly, they're going to wrinkle like this. We're going to have misalignment of the fibers, and that's really important when we think about that orthotropic nature. The other thing on this right-hand picture is we need to deal with lots of different fabric shapes. If we want to reinforce a certain area, we would cut out a different shape and we'd lay up that reinforcement separately to this overall kind of layer. So we need to know what the shape of that is going to be just to cut it out of our larger rolls. We want to know what the most efficient way of laying that reinforcement up is going to be, and that's things that the ANSYS Composite PrepPost can help us do. So this is what I was meaning with the fiber, with the wrinkling, because we're dealing with basically a soft fabric. Curved surfaces are particularly bad at this. We're going to have wrinkling. We're also going to have a change of fiber alignment as we cover these curved surfaces. So this is a demonstration of what the fiber misalignment from a 090 kind of woven material. You can see right up the top here that the fiber alignment is essentially perfect, 090 degrees. But as we pull it over this surface, you have this region where we have an awful lot of fiber misalignment. And we need to know where these regions are in our structure, because the strength in this region is going to be nowhere near the strength at the top where we just assumed the composite material was perfect. And then this is also an example of where we have some wrinkling and some folding of the composite fabric. The other really complicated thing about composites is because they're made up of different materials, their failure modes are very, very complicated. And this is only exacerbated by the fact that most composites are quite brittle. They won't display much or any plastic deformation before they go. So this is if we were loading our fibers, and our fibers are fracturing under a tensile type loading, we get quite a dramatic kind of explosive effect when the specimen will break. Under compressive loading, the fibers can crack and buckle, and we're going to have not only fracture of the fibers but delamination, which is where these plies start to peel apart. And we can see this really, really well in this delamination test. So we're squeezing this composite component and the plies are beginning to separate, and that's because the matrix material is so much weaker than the fibers. It doesn't take a lot of force to pull it apart, and this can be difficult to see in a physical inspection of a part. So it's quite dangerous when we're talking about damage resilience. So those are some of the complexities, some of the benefits of the materials, and I'm just going to go through really quickly how the ANSYS Composite PrepPost fits into a workflow to analyze these type of structures, to design your composite structure to mitigate those complexities to factor in those complexities so that we're going to have a safe structure, but also the highest performance possible. So this is the Workbench workflow. You guys might be familiar with this general layout where we're passing information from individual kind of parts of the analysis. So on the left-hand side, we've got our geometry. This will need to undergo some cleaning up to get it ready for the analysis. And this is what we'll feed into the ANSYS Composite PrepPost module. So we'll need a mesh at this stage. And then we're going to bring it into the preprocessor. We're going to do our composite definition, which is we're going to specify our layup, fiber orientations, material thicknesses, things like that. And then we're going to pass it through all that information, that composite definition, into our FEA analysis. We're going to apply our loading, whatever we need to do. And then we're going to post-process the results. So there's some things that are specific to composites that we need to look out for. Those really complicated failure modes. There's some specific tools integrated into ANSYS that's going to let us analyze for those composite specific results. This has been updated in recent releases. A lot of the post-processing has now been integrated straight into ANSYS Mechanical, so it's streamlined a lot. So I'll show you how to do that and access all those results directly from ANSYS Mechanical. All right, so I mentioned geometry cleanup. This is general to most mechanical models. We're looking at reducing the unneeded details in our CAD geometry. So we've got this vehicle, it looks awesome, but it's going to be very computationally expensive if we need to analyze every single little detail, every single little bolt, every little fillet. That's a lot of features that we need to resolve in our mesh, so it's going to be very hard to do. So we just want to pull these out. There's a lot of automated tools in Space Claim that will let us do this quickly. And then the other thing is that we need to work with shell geometry to do this ANSYS Composite PrepPost layup definition. That's something that's built into the software. It operates on shells, so we need to take our initial CAD file, whether it's solid or shell, and we need to convert it into a format that we can use. So this would be something that you might actually bring into ACP. It's a lot more basic, but it's got the features that we need to look at. It's going to be far more efficient. We've reduced a lot of the fillets and we've taken off a lot of the little features. So the next stage, I mentioned we're going to need a mesh. That's done just as normal in ANSYS Mechanical. Anything that was good for a mechanical model is going to be good for a composite model. One of the other things that we need to do, though, is we need to specify fabric shapes. I mentioned that a composite structure can be built up of lots of different fabric shapes. We need to specify these before we reach the ACP preprocessor. So the way we do that is once we've meshed our model, we need to use name selections to specify fabric shapes that we want to then bring into ACP. So whatever name selection I specify in Workbench, it will be there in ACP. So this can get quite complicated when we're dealing with a lot of different structures. This is a composite wheel model. It's been I exploded it to show the number of different fabric shapes. There would be different reinforcement areas that we're bringing into ACP. So I'll show you some of the tools in ANSYS Mechanical to specify these fabric shapes. So once we've got our mesh, we've got our fabric shapes, we're going to bring it into the ACP preprocessor. And this is the window that you'll have. So it's actually laid out quite similar to ANSYS Mechanical. So if you're familiar with that layout, you'll probably take to this quite quickly. Obviously, we have our GUI. We want to be able to visualize what we're doing directly onto our model. That's very useful, obviously. Up the top, graphics options. So we can specify views, reset views, take photos, and we have this little group of arrows here This is to help us visualize things like fiber direction, thickness directions of the material itself. Because that's so important for composite materials, we have these tools built into it to let us do it properly. And then on the left-hand side, we've got our model tree, basically exactly the same as ANSYS Mechanical. And one of the convenient things about this is that to take a model from start to finish, all you need to do is work your way down this list. So it's very, very user-friendly in that case. Up the top, first thing we need to do is material specifications. So this is essentially what type of composite material are we laying up on our structure? What are the thicknesses of that material? Element sets, the second thing that we need to deal with is the fabric shapes. So this is all brought in from mechanical, like I said. So rosettes. So these are something that will specify the reference orientations of our material. So this is a little feature that we'll put onto our structure that will specify, all right, this is our 0-degree fiber direction, this is our 90-degree fiber direction, this is the thickness direction, and then any kind of orientation that we want to do of our plies is in reference to this rosette. And then we need to bring it all together. We need to take fabric shapes and we connect them to a reference orientation. So we would do that through the orientated selection sets. And then finally, we're going to take that fabric shape and apply material to it. And this is where we're going to be specifying our ply layup sequence. So this is where you can go 0-degree ply, 45-degree ply, and build up the thickness with multiple layers. Also, units, specify unit system, that's going to be up the top. It's just a really classic mistake made in ACP. I do it all the time, that the unit system that we're working with in Workbench isn't actually brought through into ACP. So first time you open it up, just re-specify your unit system and there won't be any issues. So with our composite layup all defined in ACP, we're transferring this information across into our FEA analysis. So this is ANSYS Mechanical, and you can see here imported layer section. So this is where all of that information is of ply layup definition. So all the different individual plies, their orientations, their thicknesses is integrated into this feature here. And then we can just essentially simulate our model like any other mechanical model. So applying our boundary conditions, running the analysis, and post-processing with whatever results are going to be specific to that application. So things that are some of the post-processing features that will be really critical for a composite material. Obviously, things like stress analysis are going to be a good indicator of how safe our structure is. But because there's such a difference in strength between the fibers and the matrix, if you have a fairly modest amount of stress but loaded in a really incorrect orientation, you can damage the structure. So looking at a more complicated way of analyzing failure, essentially analyzing whether this structure is safe or not, we need to use things that are called composite failure criteria. So these are far more complicated than just a kind of yes, no on the stress. They integrate the orientation and things like that. And it's going to show you, so in this case, it's the inverse safety factor. So if we go above 1, it's not safe. If the maximum inverse safety factor is less than 1, we do have a safe structure. So we'll be able to visualize the critical locations on our structure and also the failure mode in particular that we should be worried about. So we have this notation that's going to tell us, well, in this location, we're going to have a failure of the matrix in this case. So that's the thing that we need to look out for. That's the thing that we might go back into ACP and design into our structure to slightly reinforce it in that area to make it safer. So that was a quick run through of the kind of workflow in ACP. I'm going to move over to Workbench now. I'm going to give you a quick demo of the kind of geometry preparation that you would be doing to take kind of raw CAD and get it ready for an ACP analysis. So looking at the simplifications, looking at some cleanup, I'll quickly mesh it and show you how to do those name selections to isolate the fabric shapes in mechanical, and then I'll move it over into ACP.